In this video, we're going to discuss what Gibbs free energy is and where it comes from. Well, in the last video, we talked about the entropy of the universe and its relationship to the second law of thermodynamics, basically stating that for any spontaneous process, the entropy change of the universe must increase. Well, Gibbs energy takes this equation of delta S universe and delta S system plus surroundings and puts it in a slightly more user-friendly manner. So Gibbs energy, it's derived as follows. We take our statement that the universe is equal to that of the system and surroundings and change the surroundings in terms of enthalpy. That is, the entropy of the surroundings is equal to the opposite of that of the system, so negative delta H, divided by the temperature of the surroundings. Well, rather than deal with a fraction in terms of delta H over T, we're going to multiply everything by the temperature to arrive at the negative temperature of the surroundings equals, or times this entropy change of the universe equals the negative temperature times the entropy of the system plus the enthalpy of the system. Rearranging this slightly, we arrive at the Gibbs free energy equals delta H minus T delta S. So what is Gibbs? Well, Gibbs is the same as the negative temperature of the surroundings times the change in entropy of the universe. This is a far simpler way of representing the same equation in that we have enthalpies which can easily be calculated. We have an entropy of the system which can also be calculated. And we don't have to worry about keeping track of three different entropies, that is the universe, the system, and surroundings. We're really just left with the entropy change of the system. So the Gibbs free energy of a reaction can be used to predict the spontaneity of a reaction. That is the reaction expected to be spontaneous or non-spontaneous? It doesn't mean the reaction will necessarily occur, but rather tells us that it should occur or should not occur. Recall that the activation energy is another component of whether or not a reaction can proceed. However, it is not a component of thermodynamics. If the Gibbs free energy is positive, then the reaction is non-spontaneous. If the change in Gibbs free energy is negative, then the reaction should be spontaneous. So while we can use Gibbs free energy to determine whether or not a reaction can occur or should occur, it does not tell us if it actually will, because of the activation energy. And there are a different set of conditions which can lead to spontaneous or non-spontaneous reactions as described in the chart here, which I'm not going to spend any time going over. Rather, you can just read this at your leisure and see if you can get around to predicting based off of your predictions of entropy and knowing what you know about enthalpy and whether or not the Gibbs free energy will be positive or negative, and whether or not a reaction will be spontaneous or non-spontaneous, or if it's selectively spontaneous based off of the temperature. Now, another thing that goes into determining whether or not a reaction occurs is the actual set of conditions for the experiment. And so when reactions stop, that's because there's a lack of energy causing the reaction to occur. Well, all of our discussions about thermodynamics and entropy and enthalpy have dealt with standard state conditions to this point. That is the little degree sign we've seen. When we're working with equilibrium, though, we often find that our equilibrium is not at standard state conditions. Therefore, we can say that when a reaction is out of energy, that is delta G is equal to 0 right here, then we find that the standard Gibbs energy plus RT ln of K, that is our equilibrium constant, the sum of those two things must equal 0. If the energy or the Gibbs energy is not 0, and is negative, then the reaction should still continue to occur. So at non-standard state conditions, we can say that the Gibbs energy plus the gas constant R, 8.314, times the temperature in Kelvin times the natural log of K equals 0.